In this section, we're going to look at describing linear relations. Our main focus is going to be with distance time graphs, but we're just looking at how we can actually make a description of what's going on in the model given by a graph and a relationship that is linear. So a distance time graph, we've kind of looked at them a little bit before, but what it does is just model how far an object moves from a fixed location over time. If you note the rate of change here, and here's my distance time graph, this one's going up, it's an increasing graph. The rise over run will result in the change in distance over the change in time for the rate of change. That's speed. If this was meters and seconds, it would be meters per second. Kilometers and hours, kilometers per hour. So the rate of change in a distance time graph is the speed. So an example working with this. For the graphs given, just describe the motion illustrated, what the initial value means, and the meaning of the rate of change. So here we have someone who is starting at 1 meter away from whatever measurement we're using. So the initial point, starting 1 meter away, and then travels for 5 seconds, and it's a straight line, so the speed's going to be constant because the rate of change is the speed. So how would we describe this motion? The object, whatever it is, it could be a person, could be an item, starts at a distance of 1 meter away from whatever this zero marker is, and then moves away at a constant speed of. Now, to find the constant speed, we need to get the rate of change. So we got to look on here. And so this is a good point, 0, 1. And then the only other nice point that I can explicitly tell is right here at 5 and 5. So if I just draw a little, get a right color here, unit triangle, or sorry, rate triangle, quickly. I got a run of 1, 2, 3, 4, 5. So my run is 5. My rise is 1, 2, 3, 4. So my speed is going to be the rate of change. So my rate of change is equal to the rise over run. And that is equal to 5 over 4. Now, in the previous unit, I said we usually keep our improper fractions in that as they are. And in many cases, it's good to keep the rate of change as a fraction so we can count out the rise over run. But in the case of this, it's a speed. You wouldn't tell me that he was running at 5 over 4 meters per second. What you do is actually calculate that. So you divide 5 by 4 and get a speed of 1.25. That equals 1.25. meters per second. All right, so if it makes sense to give it as a decimal, then we can convert that to a decimal. If it's just a generic situation where there is no need for a decimal, it's just working with like general x and y and equations, then we would leave it as a fraction. But in this case, it makes sense to say that the speed is 1.5 meters per second. In the next situation here, we have someone traveling away from they're starting or towards the measurement of distance. This could be someone traveling towards their home or something like that. It just depends on what we consider the starting point. The starting point of 0, but it's someone traveling at a constant speed again. So let's find our speed again. That's going to be the rise over the run. So let's find a couple points here. There is a point right here. There's a point right here. So I'll make a rate triangle. Doesn't matter if it's above or below the line as long as it's a right angle. And so we got here someone traveling 1, 2, 3 kilometers is the run. 1, 2 kilometers, and that's -2 is the rise. So the rise over run is -2 over 3, which would be 0.66. And that's going to be repeating, so 66 or 67 if we round it, and that's a negative. So negative 0.67 kilometers per hour is the speed here. So to describe this, the object moves toward the start at a speed of 0.67 kilometers per hour. Why didn't they put the negative sign there? Well, by saying we're moving towards the start, we are implying that it's moving in that downward slope, so the negative is not needed. So those are two situations of describing a constant motion with a linear graph. So this is a way to model linear motion with the graph and describe some of the motion with the rate of change. All right, here we're working without graphs and just having a situation. We want to describe the motion in the situation and then sketch a graph. So we have the motion of a balloon is rising. Its height is given by the formula h equals 1.5 t plus 2, where h is in meters and time is in seconds. So the height's in meters. So how many meters it is above the ground is going to be given by 1.5 times the number of seconds it's traveling plus 2. So if we describe that, well, let's sketch a graph first. And we'll just do a quick little sketch of the graph. And again, when we're doing a sketch, we don't need to be exact. We just want to get some key points on there. So it's going to start here, say, at 2 meters. So we'll say 2, 4, 6. And then it's 1.5 times t. So if I just make some approximate markings here, 1, 2, and 3. Let's just pick a further point down, like, well, let's pick 2. It's 1.5, so I know if I double that, I'm going to get an even number. 1.5 times 2 seconds will be 3, plus 2 is going to be 5. So that's going to be right in the middle here. It's going to be about right here. So there's a quick little sketch of the graph and its motion. It's going upwards, and this is our height, this is our time. So something like that would be a quick sketch of that. And so now if we describe that, it starts 2 meters above the ground because it's a balloon rising. So we're starting 2 meters above the ground, and it moves upwards at a constant speed of 1.5 meters per second. So from that equation, we can see there's our starting point. It starts 2 meters above, and it's going up at 1.5 meters per second, and that's what it would look like graphically. In the second situation, a boy runs home at a constant speed. His distance in meters is modeled by d equals 750 minus 5t, where time is in seconds. So if we do another quick sketch here, and let's see, it'll be, let's give that, say, 750. So that could be 1, 2, 3, 4, 5. So that's 750 divided. So that's going to be 150 down each time. So that would be 600. That would be 450. And then 300, and then I'm going to make that a broken graph because it makes sense to have a broken graph here. So there's my little sketch. I made the broken graph. We got 0, and then we'll just quickly draw a couple numbers over here. 1, 2, 3, 4 seconds. So let's just try. So it's going to start at 750. That's our initial value, and then we need another point for a quick sketch. So 5 times 4 is going to give me 20. So it's going to move down after 4 seconds. And maybe we'll even change the time here then. Let's change that scale because we're only going to go down to 730. Let's go by tens. So that looks a little bit better. We'll probably move quicker down now. So 750 minus 5 times, let's do 30. 5 times 30 is going to give me 600. So I can put a point there. And then, again, this is just a quick sketch just to kind of illustrate what's going on. It's not exact, but there's our motion. So we have, after 30 seconds, it's traveled 150 meters. The boy starts 750 meters away from home. And moves toward home at a constant 5 meters per second. So that would be a description there of our motion. So we can look at the motion and describe it based on a graph. If we're given a graph, especially with distance and time, we can find the rate of change, and that will give us our speed, or we can get the rate of change from the equation. That'll give us our speed. Our initial value can be pulled from the graph or the equation, and we can use those to describe the varying situations.